Oh, thank you.
So are the speakers here?
That was hey, good to see you. Good to see you. Yeah. Generalized.
Could they come and test it?
Yeah, let's work on all the speakers.
Jason's gonna go before me, so Jason will do.
Yeah, just
Oh, thank you.
Hey everyone, come on back in and find a seat. It's time to get started with session 2. So before we start this session, I have 2 important announcements to make. First, perhaps most importantly, I want to let everybody know that additional coffee is on the way. So we'll let you know when that's available. Should be delivered here in the next few minutes. Second, I just wanted to call your attention to the program. If you notice, on Friday afternoon, right after the last talk, we've got a very, very short closing ceremony, which will include an awards presentation. We will be naming an outstanding paper award for the meeting, and I would encourage everybody to stick around to see how that turns out. Right. So very short, just after session 9 on Friday afternoon. Right. So those 2 announcements. I'm very happy to introduce the beginning of session 2. We turn it over to Lydia Tapia, who's the chair.
Jason. Super excited to be here for a WAFR in person after the pandemic. Let me go ahead and get our first speaker to set up. Hong Wei, are we set up? Great, perfect, thank you. So they're going to talk about distributed spacing control for multiple buoyancy controlled underwater robots. So go ahead and take it away, Kong.
Hello, my name is Kong Wei. I'm a postdoc associate working at here. This work, distributed spacing control for multiple buoyancy controlled underwater robots, is done with my advisor, Dr. Drake Paley. The research is the control part of our current work, which is finding a way for a distributed system to track and observe an underwater biology system named the scattering layer. Given the dynamics of the flow and the scattering layer, our distributed system can achieve desired formation while tracking the scattering layer by the derived control algorithm. Since it is an interdisciplinary work, let me first introduce the oceanography background and the platform we are using to explore the ocean, which is interesting. I will then talk about the distributed control algorithm in detail, which may not be that interesting. The scattering layer is a layer in the ocean consisting of a variety of marine animals. It can be seen to rise and fall each day in keeping with the Dell vertical migration. It is the largest ecosystem on the planet in terms of biomass, which is estimated to be between 5,000 and 10,000 million tons. Its Dell migration makes deep scattering layer play an important role in the pelagic food webs, serving as a vehicle for transferring energy between productive surface waters and the deep sea. Importance of a scattering layer in global carbon cycle is another reason that we need to investigate it continuously. Other motivation includes military purpose, since the scattering layer always appears as false seafloor from sonar. Traditional methods of detecting scattering layer achieved by tethered echo sonar or deploying trolling net. But the echo sonar can detect and observe only specific organism. Deploying trolling net, on the other hand, may cause troll avoidance behavior, which end up with underestimation of boil mass. Trolling net thus also disturb the behavior of the organisms in the scattering layer. In our research, DriftCam, which is a buoyancy-controlled underwater robot, is applied to perform the task. DriftCam is an untethered mid-water imaging system built to collect detailed information about the ocean animals by high-resolution video at the depth as deep as 700 meters. The DriftCam is equipped with LEDs, which provide the light for its cameras in deep ocean. The device is able to adjust its own buoyancy, pumping lighter than the seawater mineral oil to or out of an external bladder here, causing the DriftCam to move up and down in the water column. Its actions can be directed either by acoustic command or autonomously following a program preloaded in its inner computer. Quietly hanging in the water, drifting along with the water movement, the DriftCam collects video of the mid-ocean organisms, such as those in the scattering layer, with minimum disturbance. So the last picture is a diving experiment done in the neutral buoyancy water tank in the University of Maryland. This video is taken by Rachel Suter, PhD student from the University of Maryland during a cruise in the Gulf of Mexico. So see, look at the DriftCam. So look at those sea creatures and the robots hanging, flowing in harmony. Okay, so consider. So now it's the boring part. Okay, considering the physical scale and the motion style of the scattering layer, it is reasonable to deploy a multi-agent network of DriftCam for this task. So the optical cameras have limited perception range, especially in the ocean. Communication range between those DriftCam also has a limitation. A swarm can cover a large-scale space, such as the scattering layer, and it is also tolerant of individual or partial network failure. Given the ocean flow field and the dynamics of the scattering layer in the horizontal and the vertical axis, our goal is to have any DriftCam achieve equal distancing D with its immediate neighbors and tracking the depth of the scattering layer. For simplicity, the flow field is modeled as a shear flow, and the depth dynamics of the scattering layer is considered as a harmonic oscillator. For full depth water column, the flow velocity field can be approximated by the combination of shear flows with varied slopes. The control input hinges on the difference between the drag force and the buoyancy. Both the DriftCam and the scattering layer bear the flow velocity in the horizontal direction. One technique that we apply is the backstepping method. It is basically designing the control force based on the result of W, which denotes the desired vertical velocity for control objective. What I'm trying to say is that once we have known what W looks like, we can then use the backstepping method to derive U here. So now let us pay attention to W, which has two tasks. One is to have equal distancing, and the other is to realize the depth tracking. We first pick a potential constructed on the sigma norm of horizontal distancing, a distance between those DriftCams. This norm is used to make zero differentiable. Then we can later prove the gradient of the potential is very key in realizing distancing control for those drift cams. At last, the tracking is achieved by a feedback controller, given the information of the depth and the vertical velocity of the scattering layer. Because of the time limitation, I just briefly introduced the proof. We first transferred the dynamics of the drift cam swarm to a new coordinate centered as its mass center. We can show that the potential does not change for this transformation. With the coordinate transformation, the task of depth tracking is divided into 2 steps. The first is achieving depth consensus for the swarm, and the second is depth tracking for the swarm mass center and the scattering layer. At the same time, we can see the gradient of the potential guarantees the network of agent converge to the global minimum of the desired configuration. This can be proved by picking a Lyapunov function candidate, applying Lascelles invariance principle. The potential function is deliberately selected, so there is no local minimum. Once we have the desired vertical velocity for the control objective, we can design the force controller by backstamping method.